Welcome to Geography 105, Weather, Climate, and You Online. This is Unit 6, Adiabatic Processes, and in this lecture we're going to take a look at what happens to these theoretical volumes of air, or what we term air parcels, as they move up and down in our atmosphere. So we'll be putting the ideas of energy and work and saturation, dew point to good use in this lecture. And you can see in this particular example here to the right, we have this theoretical box or volume of air, and as it ascends through Earth's atmosphere, it changes its temperature. In this particular case, it'll hold its dew point constant, but we'll see that that's not always the case. In this example here, the parcel expands in terms of volume, the temperature decreases until it achieves this state that we know as saturation, where the temperature equals the dew point. So it's a relatively short lecture today, but we'll be putting some of these ideas to use.
The first thing that we'll kind of focus in on this lecture is a simple law that we've probably seen before somewhere, known as the ideal gas law. The ideal gas law was actually first written in the middle 18th century by Emile Clapeyron, and later on actually formed an equation known as the Clausius-Clapeyron equation, which we still use today. The ideal gas law is very important. It essentially explains a lot of very important day-to-day applications in our lives, such as filling air or filling your tires with air, heating the air inside of a hot air balloon to make it rise. So let's take a little bit. If I play this slide one more time here, you can see the piston coming down in the cylinder, and as the piston comes down in the cylinder, the pressure increases, but the temperature also increases inside of that cylinder as well. So there's some very simple variables and interaction between variables that govern this idea between volume, pressure, and temperature. So let's go ahead and take a look at those relationships here. They are all rooted in our society. You see these every single day. They always tell you to check the air pressure in your tires before you're driving, especially if it's in the winter time. Oftentimes in the winter, your low tire pressure light will come on. As the temperature outside decreases, the pressure in your tires also tends to decrease unless you filled it. Why you would heat the air in a hot air balloon to get it to rise. All of these situations have in common that there is some relationship between temperature and pressure, and specifically density. So we're going to explain density today. We're going to explain, we've already talked a little bit about pressure and the interaction of temperature, density, and pressure, temperature, pressure, and density to kind of govern these sort of physical principles. Okay? So here's the ideal gas law at the bottom. If you want to simply write this out in your notes as the pressure of the system is equal to the density times a constant times the temperature. That constant is R in the equation here. R as a fixed value of 287. So whenever I do this with students, I kind of just like to cross out the R and just focus in on the relationships. If you cross out the R in this equation, you're left with pressure is equal to the Greek letter rho, which is density, times temperature. Okay? And I'm going to show you that in this particular equation, the units for pressure are pascals, density is kilograms per meter cubed, and temperature is in Kelvin. So when we solve this equation, we'll be using those particular units. But all the ideal gas law says is that there is a relationship between pressure, density, and temperature. And if you don't quite understand density yet, that's okay. If you don't quite understand pressure yet, that's okay. But remember, pressure was the force per unit area. We equated pressure to the weight of the air above our heads. Think of yourself in the atmospheric swimming pool, if you will. At the bottom of the swimming pool, which is where humans are located, that's where the pressure in the atmosphere is the highest. Density is very easy to explain. We'll look at that in the next couple of slides. And then temperature we've already defined as this mean molecular speed of the molecules. So if we were, faster moving molecules have a higher kinetic energy and therefore what we call as humans a higher temperature. So we've discussed these very briefly. We're going to kind of pull them all together in today's lecture and then talk about how they relate to one another. And that is the ideal gas law. Okay, so I posed this question down here in the bottom right-hand side in the orange box. What would happen if we heated up a fixed mass of air in a rigid container? So a rigid container is a container that cannot change shape or size. It just maintains the same amount of volume. So think of a Tupperware container as a rigid container. What would happen to the air inside that Tupperware if we were to heat it up? Okay. The answer would be the density would decrease and also the pressure would decrease. Okay, and that is related to the ideal gas law. So let's take a little bit more look at the ideal gas law and how it can kind of help us. In the ideal gas law, if you were to hold temperature constant, you would essentially be left with P and rho. Okay, because remember, R is the gas constant. R is already a value that does not change. So if you imagine temperature being constant, what you can do in equations when things are constant are essentially cross them out. Right? So T is constant, R is constant, and we're left with P equal rho. Pressure is equivalent to the density. So, since there are constants, we can't really say they're equal because we do have to factor in those constants. So what we say is we use the tilde sign and we say pressure is proportional to density, meaning that there is a direct relationship between pressure and density. If pressure does one thing, density must do the same thing. So if pressure goes up, density must go up. If pressure decreases, density must decrease. Okay. If you were to write this out in literal English, it would look something like this. At the same temperature, because we're holding temperature constant, air at a higher pressure, increase the P, must be more dense than air at a lower pressure. Right? So if we increase the pressure, we must increase the density. That's all we're basically saying here. If you hold temperature constant, there's a proportional or direct relationship between pressure and density. Okay? So in a little bit simpler terms down here in the yellow, at a constant temperature, an increase in air density will trigger an increase in pressure. Okay, pretty straightforward so far. What would happen if you held pressure constant? Now, the left-hand side of the equation is constant. The R is constant, so we cross out the P, we cross out the R, and we're left with equals rho T. So equal sign, density, temperature. Well, we need to come up with a relationship, so let's divide one of these to the other side. So let's just take density and divide it over to the other side, and you can imagine in your head if you're doing this or if you need to write it out on paper, 1 over rho equals T. Okay. So now we have a 1 over relationship. That indicates there is an inverse relationship between density and temperature. An inverse relationship simply says if the temperature were to increase, the density were to decrease. So whatever the left-hand side of the equation does, the right-hand side will do the opposite. Because in this case, the opposite side is in the denominator, where the right-hand side is in the numerator of the equation. So again, cross out P, cross out R, it is our constant. We're left with equals rho T. Divide a variable to the other side, and you're left with 1 over that variable equals that another variable. So it's kind of like the old 1 over A equals B sort of thing. It's an inverse relationship. In literal English, if you were to hold pressure constant, you'd come up with a statement like this. At a given atmospheric pressure meaning the pressure is staying constant, air that is cooler, so lower temperature, must have a higher density. Okay? So they're just doing the opposite. If you were to increase the temperature, you will decrease the density via the ideal gas law. Okay? So you can do all kinds of sort of things here, but just think about this for a second. A hot air balloon. Okay. If you were to increase the temperature of a hot air balloon, the air would become less dense. That makes sense. Things that are less dense will tend to float. All right? So this is why hot air balloons rise, because you increase the temperature inside the hot air balloon. You're staying at a relatively constant pressure if you want to hover in the atmosphere. So if you increase the temperature, you will decrease the density, and that hot air balloon will want to float. So the old rule of thumb here is that warm air rises and cool air tends to want to sink. Right? Warm air rises because it is less dense. Cool air sinks because it is more dense. Okay. One question that we really try to answer as meteorologists is, when is the air going to rise? We want to know when the air is going upward, okay, toward the stars, towards straight up. Because if the air moves up in the atmosphere, it has the potential to cool. We talked about the fact that as you increase in the atmosphere, temperature decreases. Right? The tops of mountains have snow peaks. As you go up in an airplane, the temperature gets very cold in the troposphere. If the air is lifted upward, it will also cool and has the potential to cool to the dew point. We said if the temperature equals the dew point temperature, we can get saturation, right? And potentially condensation and maybe even precipitation to fall. So, as meteorologists, we're always trying to figure out when it's going to rain, right? When is the air going to rise? And if we do this, we can come up with some ways to try to understand whether or not the air is going to want to rise or sink based on comparing the parcel temperature to the surrounding environment. So I'll talk a little bit more about this in a second. This does come with a little bit of a price. It involves a lot of math and some difficult concepts. And it would be a lot easier without water vapor, but then we wouldn't be able to live here. So water vapor makes this a little bit challenging. But once you understand this very basic principles here, and we're not going to go too much into the math, we're just going to kind of show some lapse rates and some things and some comparisons and graphs that you can draw. But once you're able to do this, it explains a lot about temperature and precipitation across the United States, which is very important for weather and climate. In order to achieve clouds, okay, one of three things needs to happen. You essentially need to get the temperature equal to the dew point temperature. So the energy content in the atmosphere, this idea of temperature, this average molecular speed, must be equivalent to the amount of moisture content in the air. So if we have a temperature of 73 and a dew point of 70, that air is not saturated. Remember, the dew point temperature will never be greater than the temperature. So how can we get the temperature equal to the dew point temperature? We can either A, add moisture, so that would increase the dew point to the temperature. So in this case, let me give you some examples of this. Let's say we had a temperature of 70 F and a dew point of 65 or 66 F. We could simply increase the bottom number to 70 in order to achieve saturation. We could also take the top number, the temperature, and cool the temperature to the dew point temperature, and we could also achieve saturation that way. There's one other way that we're not going to talk necessarily about today, but we'll talk a little bit more about it when we get to the clouds lecture, is mixing very, very warm air with very, very cool air. This happens a lot. You probably noticed this in the summertime if you've ever opened up the freezer in your house and you see the air come out of the freezer and immediately sinks towards the ground and you get kind of like this saturation going on. You see this in the wintertime when you're outside and it's very, very cold and you breathe and you see the evaporation steam fog coming out of your mouth. You're mixing very, very warm air inside your body with the very cold air outside that also can create condensation that way. So there's kind of three processes going on here. Today, we are going to focus mostly on this bottom one, simply lowering the temperature to the dew point temperature. So we're going to take that top number, the temperature, and we're going to try to drop it to the dew point in order to achieve saturation. All right, two new terms. You're going to get introduced to these in your weather studies manual in your reading, but I want to make sure that we define these. The first is diabatic and the second is adiabatic, so make sure you put these two terms down in your notes. These are important for the exams. So diabatic and adiabatic, and we're going to talk about a diabatic process versus an adiabatic process. Okay. A diabatic process is rather simple. The definition of a diabatic process is that energy is either added or removed from the system. Okay? So we have this sort of system. You can think of the system over on the top right-hand image is the pot on the stove. We're simply providing energy to that system from the cooktop burner through conduction of the pan. We're adding energy to the system in that case in order to get the water to boil. There are also other examples of diabatic processes in the atmosphere. This is basically, there's just sort of an energy exchange. You can imagine air passing over very warm or very cold water. Right at the surface, there will be an energy exchange between the air and the surface. Since there is energy added or removed from that system, we call these diabatic processes. Diabatic processes are very important for fog, but not for clouds. Fog is just a cloud at the surface. Okay, so you can see this image down here, the Golden Gate Bridge. We see a lot of advection fog going on in the San Francisco Bay, but this is because air is passing over the relatively cold water and it's being cooled to the dew point temperature. Okay, so you're getting clouds at the surface. We're going to see that diabatic processes are really only important at the surface, so they will provide things like fog, but they are not going to get you clouds. We will be looking for a different process in order to get us clouds. That process is an adiabatic process, and an adiabatic is just the opposite of a diabatic. An adiabatic process is a process in which no heat is added or removed from the system. So in a diabatic process, we were adding or removing heat. In an adiabatic process, we are not adding any heat. Now this confuses students a little bit because they think that the temperature can therefore not change, and that is not true. Okay, we have this system, right? We have this volume of air, this cloud up in the sky. We can move energy around in the system in the terms of different temperatures and different dew points, but we cannot change the energy content. We're not adding energy content from it. We're not taking it away. So it might manifest itself in different ways. For example, in this image on the right-hand side, we have this theoretical parcel or box of air. As we lift the box of air, the temperature decreases. So you're saying, well, there's got to be heat moved through the system. Actually not. The system is the box, and what happens to the box as it rises, you can see it's expanding. Okay, so the volume is increasing as the temperature decreases and kind of negates this difference of a lower temperature. So even though we have a lower temperature, we're over a much larger volume, and the dew point in this case particularly stayed the same. So even though, right, we might see a sensible difference in the temperature, other processes are going on. That energy, if you will, is kind of just being shifted in a different portion of the parcel. It's not necessarily being added or removed from the system. So when we talk about an adiabatic process, the easiest thing to try to imagine is that nothing comes into the parcel and nothing goes out. The parcel can change characteristics, but no energy is coming in and none is leaving. We're not putting a flame here and heating up the box, okay? And we're not changing the box in terms of its characteristics. If we were to go up with the box and achieved some sort of state and came down with the box, we would achieve the same sort of initial state that we initially had of 78 over 55. So I'm going to show you a little bit more about this adiabatic idea here in just a second. Why are adiabatic processes so important? They are so important for cloud formation. They are the reason we have clouds in the atmosphere. Adiabatic temperature changes are linear. Okay, so when air expands, it cools. As we lift up this parcel of air from the surface to aloft, the temperature will decrease because we're going higher up in the atmosphere, but the volume will also increase. So when air is cooling, it will expand, and when it is warming, it will compress. So you kind of think of this idea of the piston, right? If you were to shove air inside of a piston, or if you ever taken a water bottle and squeezed it, the air inside of the water bottle would warm up in terms of temperature because you're constricting the volume. So when we increase temperature, we will be constricting the volume of the box or compressing it. When we lift a parcel of air, the volume of the box will expand, and this expansion also allows a cooling to take place. Okay, so this is an adiabatic sort of process. In a very simple schematic diagram here, this is just kind of explains an adiabatic process. It's a nice linear process. As air rises, you can see the volume here of the parcel of air begins to expand, and the temperature decreases as it goes up. And as it comes down the other side, the parcel will compress and also warm. So there's kind of this expansion compression sort of line here that as we go up in altitude, there's a predictable decrease in the amount of temperature. So if we were to start at this dot right here, we were to lift the parcel up a certain amount of distance, we would decrease the amount of temperature, right? Or if you want to think about it this way, right? Up one, there's a slope of a line, right? As we increase the altitude, we decrease. Increase the altitude, we decrease the temperature. If we come down in altitude, we increase the temperature. Down, increase, down, increase. This is this idea of an adiabatic process. So adiabatic process, again, expansion in cooling or contraction or compression in heating in an adiabatic process. We've already discussed lapse rates in this course when we talked about the d banana, d time, so the change in temperature with respect to time. In this case, lapse rate is the change in temperature with respect to altitude. And we're going to take a look at different lapse rates in the atmosphere versus the actual temperature of the parcel. So we're going to call the parcel Wally. In class, if you were to take this Earth 1110 version in class, I have a little yellow ball. His name is Wally, just like the Walmart character. We lift Wally up and down in the atmosphere to see how his characteristics change, and we compare the temperature of Wally inside of the theoretical box to the outside ambient air temperature to see if Wally will want to rise or to want to sink. So this is a fairly simple concept. If Wally is warmer than the outside environment, he's going to want to rise. If Wally is cooler than the surrounding environment, he'll want to sink. So again, warm air rises and cool air sinks. So we're going to take a look at Wally's temperature, the air parcel, versus the surrounding atmosphere to see if the air will want to rise or sink. And obviously that's very important. We just talked about the need to want to understand when the parcel of air will want to rise. Okay, so again, the definition of a lapse rate, this should be in your notes somewhere. The lapse rate is the rate of change in temperature with respect to height or respect to altitude. Here's an example of an air parcel following what we call the dry adiabatic lapse rate. This is very important to understand this. Okay, so the first thing that you're going to want to ask yourself when we start to do these problems is the parcel saturated? You're going to ask that question. Is the parcel saturated? How do you know if the parcel is saturated? You need to compare the temperature and the dew point. If the temperature is equivalent to the dew point, then the answer to that question is yes. The parcel is saturated. If the temperature is not equal to the dew point temperature, the answer is no. The parcel is not saturated. Okay. There's some very simple rules of thumb governing how the temperature of a parcel changes as it goes up and down in the atmosphere. It actually makes sense when you think about this stuff. The dry adiabatic lapse rate is simply the lapse rate or the change in temperature with respect to height that the parcel will experience if it is dry. Dry meaning the parcel is not saturated. Okay? So the parcel, Wally, will follow the dry adiabatic lapse rate if the parcel is unsaturated. Okay? It can still have moisture, it just means the temperature is not equal to the dew point temperature. The value for the DALR, the dry adiabatic lapse rate, is 10 degrees Celsius per 1 kilometer. There's kind of a negative sign implied here because we know that the temperature decreases in the troposphere, so we kind of just ignore the fact that that is negative. But indeed, for every 1 kilometer you ascend into the atmosphere, the temperature will fall at about 10 degrees Celsius if the parcel is unsaturated. So don't worry about the outside air. Right now we're only focusing on this parcel, okay, a Wally, a theoretical volume of air. Do not get caught up in the outside temperature yet. We haven't focused on the ambient sort of environmental temperature yet. All we're doing now is saying we have this theoretical box of air at the surface. I want to know how the temperature characteristics inside of that box change if I were to lift the parcel of air. Okay? And the answer to this is very simple. if it is dry, it's going to follow a rate of 10 degrees C per kilometer. So if I were to start here at the surface with Wally, a parcel of air, at 10 degrees Celsius. So the x-axis is temperature, the y-axis is altitude, increasing as we go up. If we were to take Wally, lift Wally 1 kilometer upwards, Wally would cool at a rate of 10. Right? So I go from 10 to 0, subtract another 10, subtract another 10. By the time I get to 3 kilometers or 3,000 meters, the temperature of the parcel has decreased to minus 20 degrees Celsius from its initial state at 10 degrees C. So basically up 1 kilometer, down 10 degrees Celsius. Up 1 kilometer, subtract 10. Up 1, subtract 10, etc., etc. You would follow the dry adiabatic lapse rate until the temperature of the parcel equals the dew point temperature. And then we'll see what happens after we hit that particular value. Once we achieve saturation, so let's say we were to lift the parcel of air, its temperature initially was 10 degrees Celsius, its dew point was 0 degrees Celsius. At the surface, we'd ask ourselves, is the parcel saturated? The answer to that would be no, because the temperature is not equivalent to the dew point temperature. However, if we were to follow the dry adiabatic lapse rate up 1 kilometer, the new parcel temperature would be 0 degrees C, the dew point would also be 0 C, and now we've achieved saturation. Okay, so condensation will begin inside of the parcel at that level. Once condensation or saturation begins to take place, we will not follow the DALR anymore. We will now follow the saturated adiabatic lapse rate, or the SALR. Okay. In this class, we are going to assume the saturated adiabatic lapse rate. I'm just going to change this right now to make this easy for you. Let's just assume for this particular class that the saturated adiabatic lapse rate is 5 degrees Celsius. Meaning that once we achieve saturation, we will not follow this 1 kilometer 10 degrees C, 1 kilometer 10 degrees C anymore. Instead, we will go 1 kilometer 5, 1 kilometer 5. Okay, so the moral of the story here is that if the parcel is saturated, it will cool at a slower rate than drier air. Okay, there's a reason for this that we'll talk about later on in the semester, but we need to be familiar. I guess, let's just bring this up right now. Maybe you have some ideas as to why parcels will cool at a slower rate if they are saturated versus being dry. So if you can come up with some of those things, maybe write them down. So just take a second to think about this. Why does air that is saturated or has moisture content in it cool at a slower rate than air that is dry? A couple of the answers that come up very commonly in class is that, well, water has a high specific heat and it holds its heat content longer. That's thinking along the right lines, but it's actually a little bit incorrect. The reason that air cools at a slower rate if it is saturated, so the reason the SALR is 5 versus the DALR, which is 10, is because of latent heat release inside of the parcel. As the air, right, as we change phase, right, down here we have air in the water, we have water vapor in the air that is not in liquid form yet. As we go through this condensation process, recall that condensation is a warming process and gives off energy inside of the parcel. So what actually happens is as the parcel kind of changes state from water vapor to liquid water, as this condensation process happens, it actually releases heat inside of the parcel and goes back to sort of warm the temperature. And if it warms the temperature, it cools at a little bit of a slower rate. So this is kind of complicated. Okay, I don't want you to be like, whoa, this is really this is too difficult. It's not difficult. Okay, it's very simple to remember this. The DALR is 10, the SALR is 5. Why does saturated or wet air cool at a slower rate? It cools at a slower rate because as the air condenses, it releases latent energy inside. Remember that latent heat is hidden. Okay, so as condensation occurs, it releases energy and it actually goes into warming the parcel. And if it goes into warming the parcel, well, of course, if it's warming, it's going to cool at a slower rate. Okay, remember that no matter what happens, as a parcel goes up, it's going to cool. It's just how fast is it going to cool? Is it going to cool at the dry rate of 10? Or is there condensation going on inside the parcel, which is helping to warm the parcel and cool it at a slower rate? Okay, so moist parcels, we're going to say cool at 5. That'll be really easy for our mathematics. Dry parcels cool at 10. So there's the SALR and the DALR. DALR is 10 degrees Celsius per kilometer. The SALR is 5 degrees Celsius per 1 kilometer. So we take the DALR, we take the SALR, and then what we can do is actually compare the parcel to the surrounding environment. Okay, so in your notes, this is what I would like you to do. DALR equals 10 degrees C per 1 kilometer. SALR equals 5 degrees C per 1 kilometer. And then this new one, the ELR, the environmental lapse rate, equals question mark. Okay, question mark. We don't necessarily know what the environmental lapse rate is. Okay, the environmental lapse rate varies in space and time. So very important here, the environmental lapse rate is variable in space and time. This is why the weather changes. If the lapse rate of the environment was always the same, we'd have the same weather all the time. In order to measure the environmental lapse rate, we actually send up weather balloons. So you can see this young lady here. She has a helium-filled balloon with a parachute and a little sensor on it. We have lots of upper air stations where we launch these upper air weather balloons. They take measurements of wind speed, wind direction, temperature, pressure, humidity, dew point, etc. They radio them back to the surface, and then we can get an idea of the stability of the atmosphere. Okay, so let me take you to our weather website if you've already haven't seen this before. I might have to copy this. Let's do this here really quick. No, that one's not working. Let me go to our new one here. All right, so I have our weather website up here, the weather.cod.edu, and I'm going to go to, this is obviously not going to be the same for you because it won't be current, but I'm going to go to analysis data. I want to show you where you can find this stuff. On the left-hand side, we have a bunch of different maps under analysis products. I'm going to go to upper air soundings, and I'm going to show you here, this is the map across the United States of all the locations where we launch weather balloons. We launch weather balloons across the United States, well, really across the world. We do it twice per day, once in the morning at about 6 o'clock and once at night at 6 p.m. So 6A and 6P, this is depending on daylight savings time, we launch these weather balloons. The closest weather balloon to us here in Chicago is probably the weather balloon out in Davenport. We also have one downstate in Lincoln, Illinois. You can see there's no upper air observations across Indiana or Kentucky. So we do have some big gaps in the upper air observation network. But this upper air observation network is vital to our forecasting skills. And so if I go click on one of these icons here, I'll go out to the Davenport sounding. And what I'm showing you here is basically the weather balloon data that is radioed back from this radiosonde launch. So as the weather balloon went up, it reported wind speeds and wind directions. It reported the red line here of temperature. It reported the dew point line. This blue line is a theoretical parcel, which we'll get into later on in the semester. But you can see that, you know, the red line is probably the most important to focus here on. You can see how the temperature changes with respect to height in Davenport. That's going to be quite a bit different than the way the temperature changes with respect to height, say, out in Albuquerque, New Mexico. So you can see the line's different, the winds are different, the green line, the dew point is different. So the moral of the story here is that depending on where you are across the globe and depending on when the time of the day it is, etc., these lapse rates of the environment are going to change pretty rapidly. You can imagine the sun comes out, it heats up the surface of the earth, and you know, we're only taking these weather balloons observations twice a day, so we're really not getting a great idea of exactly how the atmosphere is changing. But it's very important to understand that these environmental lapse rates are constantly changing. Okay, so what we need to do, we have basically two fixed values. The DALR never changes, the SALR never changes. We need to pretty much compare the parcel's temperature at a given altitude to the ambient surrounding environment. And that is going to determine our stability. So here's an example here of this weather balloon. Again, another one that I would just show you. A plot of temperature and dew point. And you might ask yourself, I love looking at these plots. I do this every single morning, and I ask myself, I wonder where the clouds are going to be in terms of the vertical today. So you can see the left-hand side, the scale here starts at the surface of the Earth, goes up to about 15 kilometers. So the troposphere is about right here. You can see the troposphere on this particular day on September 14th, 2009 in the morning. This is 12 UTC, which is about 6 o'clock in the morning. The troposphere, the tropopause, if you will, actually was right around 13 kilometers or so. How do I know that? I can see the temperatures decreasing and all of a sudden they stop and they start to increase again. So that's got to be the top of the tropopause, the top of the troposphere, known as the tropopause. So as you get up into here, that's the stratosphere. That's pretty easy to see that. The rest of this, you can kind of see the temperatures slowly decreasing with height, and they hit the troposphere and start to increase again. We also have this inversion or temperature increase near the surface. Is also very common in the fall and the winter across the mid-latitudes. And I like to take a look at these plots and go, I wonder if I know exactly where the clouds are forming in terms of the vertical today. You can imagine this would be very important for a pilot. If a pilot was flying around 3 kilometers off the surface on a day like this, there would be no clouds. The temperature and the dew point are not even close together. I ask you though, where might there be clouds on this particular day? And the answer is, the clouds might be right at the surface. We might be experiencing some fog. This sounding is from ILX, which is Lincoln, Illinois. The dew point is 50, the temperature is 50, so the air is saturated right at the surface of the Earth, meaning that if there are any clouds on this particular day, they would be right at the surface. So you can imagine yourself, if you were taking off in an airplane, you might have fog at the surface, and then as soon as you pull up off the surface, you might break through that cloud deck, and you'd have clear skies the rest of the way. Nowhere else on this particular temperature, or nowhere else on this particular sounding, is the temperature coming even close to intersecting the dew point temperature. So therefore, we have a pretty kind of clean air, if you will. There's no saturation going on above that, and therefore there's no clouds. Okay? So, just to recap what we've done so far, we talked about the ideal gas law, density, which was, again, density was described as the mass per unit of volume. Density decreases as you go up in the atmosphere. We have this gas constant, we have temperature, we talked about the relationships between pressure and density. We talked about an adiabatic versus diabatic process. Simply remember that diabatic does have some sort of energy exchange, and adiabatic process does not. And now we're going to go into talking a little bit about this idea of stability. If we want to figure out how stable or unstable the atmosphere is, when I say the atmosphere is unstable, I mean it's restless. Things are going to happen. Thunderstorms are going to form, rain, precipitation, clouds, etc. The air is unstable if it wants to rise. So we want to basically determine down here the temperature differences between the air parcel and the surrounding atmosphere. If the air parcel is warmer than its surrounding environment, it will want to rise, just like a hot air balloon. Okay? So if you're having difficulty with this idea of Wally or the air parcel, just think of a hot air balloon. Okay? Is the hot air balloon warmer than its surroundings? If the answer is yes, it will rise. If the answer is no, it will sink. If the answer is it's the same, then the hot air balloon is just going to sit there and hover. Let's take a look at some examples comparing a hot air balloon to its surrounding environment in order to determine stability. Okay? So we are going to come back and talk more about stability in another lecture. I'm not going to focus particularly on stability today, but I want to acquaint you with parcels and this idea of comparing to the surrounding environment, because it is going to become very important and later on in the lecture that is somewhat difficult to understand if you don't understand this idea of adiabatic processes. Okay? So, in the top example here, in A, I have a surface temperature of 10 degrees Celsius. If you go just off the surface, the air temperature is 9.5 degrees Celsius. And so about every 100 meters, the air temperature is cooling a half a degree C. If it's cooling a half a degree C per 100 meters, that means that it's cooling about 5 degrees C per 1 kilometer, right? We just move the decimal point, add a 0, it's cooling at 5 degrees C per 1 kilometer. That's the environment, okay? A dry parcel is going to cool at 1 degree C per 1 kilometer. Okay, I'm not sure why that 5 is there, ignore that. It will cool at 1 degree C per 100 meters. So the dry adiabatic lapse rate is very simple. It's 10 degrees C per 1 kilometer or 1 degree C per 100 meters. So over here on the left, if this is a balloon, it starts at the surface at 10, it will go to 9, and then to 8. So by the time we get to 200 meters, the balloon's temperature is 8. With an environmental lapse rate of 0.5, at that same 200 meters, the air temperature is 9. Compare the balloon to the air temperature. The balloon is colder. What is the balloon going to want to do in this example? It's going to want to sink. Okay, this is actually a stable atmosphere, and we'll get more to that stability later on. So you might be asking yourself, what the heck is going to cause these parcels to rise? Okay, the answer is there are 4 lifting mechanisms. This is important for the exam. Okay, what mechanisms determine whether or not the air will rise? Okay, so what's going to force the air to get started lifting anyway? We're going to see actually there's processes where the air will just take off and accelerate on its own, especially in really crazy situations like tornadoes, hurricanes, and thunderstorms. The air can actually be so unstable that it will just accelerate upwards on its own. It doesn't really need much of a lifting mechanism. The first one is convection. I've already talked about convection in this class. Convection is the idea of vertical movement in a fluid, so you can think of convection kind of as a lava lamp. We have radiation incoming from the sun. It hits the surface of the earth. It transmits to the surface. It conducts energy to the lower portion of the atmosphere. That's conduction. And then throughout the rest of the vertical fluid of the atmosphere, it convects. So these little thermals. If you ever heard of the word thermal before, a thermal is a great idea of convection. These little bubbles of air that are rising and sinking based on their density. We could have lift due to topography, or what we call orographic uplift. As air flows toward a mountain, it can't go into the mountain or under the mountain. It's forced up and over the mountain. And often what you will see on the windward side of the mountain, that's where all the clouds and precipitation will be. So you've probably heard of the rain shadow effect before. If you've ever visited Hawaii, this is very prominent in the Hawaiian Islands, places like Maui, Kauai, or the Big Island of Hawaii. As the air impacts one side of the mountain, it will rise, it will lift. You get a lot of vegetation, a lot of biodiversity on the windward side, and on the leeward side, the air sinks, warms, and compresses, and it's like desert conditions on the other side. So it's kind of almost like wringing out the parcel like a squeegee on this side. As the air is lifted, all the moisture is kind of squeezed out of it. We're going to talk more about topography later on in this particular lecture. We're going to kind of focus in on actually on the orographic uplift today. We have an entire lecture coming up just on fronts and how fronts play a role in displacing and lifting air. So fronts kind of act like this large snowplow. As the cold air advances, the warm air kind of rides up and over it due to differences in density, and you can get lift in air due to these fronts. So if you're not too familiar with fronts yet, no worries. We're going to talk about frontal lifting. And also you can just have air of opposing wind directions. You could imagine if at the surface, let's say in Chicago, you have air coming off the lake from the easterly direction, and you have wind out on the western suburbs coming from the west. Wherever that air collides, it's coming in opposite directions. It can't go into the ground. It must collide and go upward. We call that surface convergence. So if we have converging winds or winds from opposing directions at the surface of the earth, that air cannot go into the ground. It must it collides and it moves upward in a fashion known as surface convergence. That can also help get clouds formed by air moving upwards. So we're all of these are kind of, how can the air start moving upward? So we can heat the surface so intensely that we get the air to start rising on its own. We can force air up and over a mountain. We can have these frontal features that come through and lift the air, frontal wedging or frontal lifting, or we could just have winds from opposing directions. All 4 of these play a role in lifting the air, and we're going to be very interested in all four of these lifting mechanisms when we talk about stability. So right there at the bottom, that last bullet point, we're going to see later on in this class how stability and lapse rates play a role in how quote-unquote easily an air parcel is displaced. We're going to see that if the air parcel is already very, very warm, okay, let's say we have a very, very warm air parcel sitting over Chicago. If we get a little bit of surface convergence, if that air is already really, really warm, you can imagine it's going to want to rise anyway on its own. Then you can get really explosive upward movement or upward development, and that's these billowing, towering thunderstorms that we often see here in the summertime in Chicago. So we're going to talk more and more about this stability and kind of this ease of parcel being displaced later on in the stability lecture. So just please write down these four lifting mechanisms and keep them in the back of your mind as we move forward in this class. To kind of cap off the lecture today, I want to focus on the second of the lifting mechanisms, which is the orographic uplift or the topographic uplift. I want to introduce to you something called the mountain problem, and I want to basically show you how air parcels change as they move up and over mountains. We don't get to deal too much with mountains here in the Midwest, but certainly if you were to move somewhere like Colorado, Washington, California, anywhere where we had large topographic features that influence clouds and weather patterns, you're going to be kind of, you'll see this sort of rain shadow effect. If you've ever driven through the Cascades in Washington, it's probably one of the greatest examples in the country of rain shadow effect. You'll see exactly why this happens. So let me show you just a simple example here of how air parcels can change as they move up and over mountains. And you may want to sketch this out and draw yourself a picture of a mountain and kind of talk this through with me as we go here. So feel free to pause the lecture, draw yourself a mountain and label the mountain up to 3 kilometers, and then we'll kind of come down the other side and see how the air parcel changes as it goes up and over the mountain. So in this particular example, I just drew this out in PowerPoint to try to give you an idea of what might happen here. I have to give you kind of 3 pieces of information. I need to give you the temperature of the parcel, which I've done. I need to give you the dew point of the temperature of the parcel, which I've done, and also the temperature of the surrounding environment. Okay? The temperature of the surrounding environment is not going to be too big of a deal right at this moment. So for this particular example, let's just go ahead and kind of ignore the temperature of the environment right now and just focus in on the temperature of the parcel and the dew point temperature of the parcel. So temperature is abbreviated by T. I have T sub ENV, which is temperature of the environment. I have temperature of the parcel, and I have T sub D of the parcel. That's the dew point temperature of the parcel. So temperature and dew point, and again, whenever you see this in meteorology, the left side is going to be the temperature, the right side is going to be the dew point. Sometimes it's expressed as a fraction, where the numerator is the temperature and the denominator is the dew point. Okay? So, how will an air parcel change as we lift it up and over a mountain? Okay, great. We're going to go up one side of the mountain here and see how this changes. At the surface, the very first question, like I said, that you're going to want to ask yourself, is the parcel saturated? The answer to that is no. The temperature and the dew point are not equal. Okay. If it is not equal, we follow the DALR. The DALR is 10 degrees Celsius for every 1 kilometer that I ascend. So if I were to lift the parcel up 1 kilometer, the new temperature would decrease to 16 degrees Celsius, from 26 to 16. I have not changed the moisture content because the parcel is unsaturated. So the dew point temperature remains the same. Okay? So at 1 kilometer, the temperature is equal to 16. The dew point is equal to 16. Guess what? 16 equals 16. We've now created a cloud. Condensation is beginning to form at 1 kilometer. Okay? I ask myself the question, is the parcel saturated? The answer is yes. I will now follow the saturated adiabatic lapse rate of 5 degrees C the rest of the way up the mountain. Okay? So I decrease 5, I decrease 5. I lost 5 degrees Celsius with the dew point. What happened? I squeezed some of that moisture out. Recall that the dew point temperature can never be greater than the temperature. So as the temperature decreases, the dew point will also decrease the rest of the way up the mountain. And where is that moisture content going? It's not a cloud anymore. We have precipitation ongoing. Some of that moisture content is falling out of the cloud. Okay. So I subtract 5. I'm now down to 11. I subtract another 5. At 3 kilometers, the temperature of the parcel is 6. The dew point temperature of the parcel is also 6. I'm still saturated. I've now squeezed quite a bit of moisture, all the way from 16 degrees C down to 6 degrees Celsius in terms of moisture content of the parcel. Okay, now here's the easy part. I come down the other side of the mountain. I was at 6.6. I cannot gain any more dew point back. I cannot gain any more moisture content. I've lost it. It's precipitated out of the cloud. So you immediately take your dew point and bring it all the way to the surface. Okay? You will continue down the other side of the mountain warming at the dry adiabatic lapse rate. Right? We're coming down in altitude, so the parcel is compressing, and it also must be warming. We increase now at the dry adiabatic lapse rate the rest of the way down. So from 3 to 2 kilometers, I add 10. 2 to 1, I add 10. 1 to 0, I add 10. My final temperature and dew point, final temperature 36 C, final dew point temperature 6 degrees Celsius. Compare those two values to your initial of 26 and 16. So 26.16 initial, 36.6 post, or on the other side of the mountain. And you will see that the end result is a warmer and drier parcel on the other side of the mountain. Okay, so just so we're clear here, the side that the wind hits is the windward side. The desert-like conditions are found on the leeward side. So wherever the air is rising up or the wind is hitting it and being forced up and over, that is the windward side of the mountain. When the air comes down the other side, that is the leeward side. So where there's not very few clouds and precipitation and very little vegetation will be found on the leeward side, as opposed to the windward side where the air is hitting the mountain and rising up. Okay, so the windward sides of mountains will always have lots of nice, here you go, upslope sides, the windward sides, cool, cloudy, wet, lots of vegetation. The leeward sides or the downwind sides are sunny, dry, and often very warm with little vegetation. Why? Because essentially what has happened is you've squeegeed out, or you've kind of wrung out a lot of the moisture in the parcel by forcing it up and over the mountains. The higher the mountain, the more drastic, the warmer the contrast is going to be between the initial conditions and the warmer and drier conditions on the other side. So you don't really see great rain shadow effects in the Appalachian Mountains because the mountains are simply just not high enough. The higher the mountains, like the Cascades and the Rockies, the much greater the rain shadow effect. Here's a really great example of the rain shadow effect in Mount Waiala'i in Hawaii. So this is Mount Edinburgh, but it goes really well for the idea of Mount Waiala'i. Take a look at Mount Waiala'i. Mount Waiala'i is situated on the island of Kauai in Hawaii. It's only about 5,000 feet above sea level, but you have a lot of moisture because you're surrounded by the Pacific Ocean. They get about 40 feet of rainfall on the windward side of the mountain. So where the airflow is being forced up, lots of trees, lots of vegetation, 40 feet of precipitation on the windward side. On the leeward side, they only get about 20 inches every year. So there's this giant rain shadow effect where the air must come down, right? The air comes down, it warms, it compresses dry adiabatically, and you get very little precipitation on the windward side, or the leeward side of the mountain. So this adiabatic processes really describe rain shadow effects very nicely. If you take a look globally at mountain chains, we're going to take a look at more on precipitation. You can see a lot of the precipitation across the world is really focused in the tropical regions, but you can see some really great rain shadow effects here. The Andes Mountains near Chile and Argentina really do this nicely. You can see lack of precipitation in the Intermountain West because of the Rockies creating rain shadows. And then downwind. So this is more global. Kind of ignore this slide for now. We're going to come back and talk more about average annual precipitation. But if we focus in on the United States, take a look at the rain shadow effect here across the Cascades up in Washington. You can actually draw a line right here, right where the Cascades are. The predominant flow of the wind across the United States is from west to east. So as the wind comes on shore from the Pacific Ocean and hits the Cascade Mountains, which are situated north-south here across central Washington, they get about 80 to 120 inches of precipitation on the windward sides. If you go just on the other side of the mountains, though, you're down talking maybe less than a foot of precipitation per year, 8 to 12, maybe even 4 to 8 inches of precipitation on the leeward sides of the mountains. You can see that the rain shadow effect is not that great in the Appalachians because they're not as tall, and the moisture can kind of get in on both sides of the mountains here, so it's not really that great of a rain shadow effect. But you can see the other rain shadow effects in some other locations here, but one of the greatest rain shadows effects in the country is along the Cascade Mountains. Okay, so we will talk more about the stability in the stability lecture coming up. But I just want to introduce you to the idea of a diabatic versus an adiabatic process and just get you acquainted with the ideal gas law, as there are some questions about those on the exams.